Good day, students. Today we shall look into interference of light and the nature of fringes in a wedge-shaped film. Now, what is a wedge-shaped film? A thin film having zero thickness at one end and progressively increasing thickness at the other end is called a wedge-shaped film. Now, two glass slides resting on each other at one edge and separated by a thin spacer at the other edge, it forms an air wedge. So how is it formed? Here we have one glass slide, and on one side we place a thin wire or a thin sheet that acts as a spacer. It creates a space. Now if we place another glass slide on top of it, see, we form a wedge shape. And the space created between the glass slides, it is having the medium of air, hence this is called an air wedge. Okay, now the wedge angle usually, theta, it is this angle, it is usually less than that of a degree. It will only be a fraction of a degree. It is very, very small. So what happens here is coherent rays reflected from the top surface and bottom surface of the air film appear to diverge from a point near the film. So what happens is when monochromatic light falls upon this wedge, okay, when it meets the top surface of this air wedge, a part of it gets reflected and another part gets transmitted. The transmitted light again gets reflected from the bottom glass slide, and these two reflected rays happen to interfere to produce an interference pattern. Since these two reflected rays are produced from a single source, they are coherent rays. Okay, so these two coherent reflected rays actually they appear to diverge from a point near the film, below the film. Now the path difference between these reflected rays, it will vary along the length of the film. Okay, so if we see the path difference between the reflected rays, at this point, the path difference will be large, whereas at this point, the path difference will be small. Okay, so depending upon the length of the film, the path difference between the reflected rays will vary. Here, the thickness of the glass plate does not come into consideration. It does not have any meaning here. So the glass plate can have any thickness. This is usually the case because the path difference will be in the range of nanometers or maximum micrometers, whereas the glass plate usually has a thickness of, yes, you know, it may be centimeters. Okay, so these are completely different dimensions. Glass plate is in centimeters, so actually it is a very thick plate, it is a very thick film, so interference cannot happen from the top and bottom surface of a single glass slide. Hence the thickness of glass plate does not come into consideration here. Now, the reflected rays from the top and bottom of this air wedge, they interfere to produce alternate, equidistant, bright and dark fringes. Now, the condition for bright fringes, the path difference 2 mu t is equal to odd integral multiple of half wavelength, that is 2n plus 1 into lambda by 2, where n can have any integer values 0, 1, 2, 3, etc. The condition for dark fringe is given as path difference 2 mu t is equal to integral multiple of lambda, that is n lambda, where n can have any values, any integer values 0, 1, 2, 3, etc. So when light is incident upon this air wedge in an almost perpendicular manner, okay, the light gets reflected from the air wedge as shown here. See, from the top of the air wedge, light is deviated to a particular angle, and from the bottom of the air wedge, light is getting reflected exactly perpendicular in the opposite direction. So these two beams, they are slightly diverged from each other, and they appear to diverge from a point near the film over here. Now here, in the condition for constructive or destructive interference, the path difference, actual path difference is 2 mu t cos r. Here, since light is almost falling perpendicularly upon this air wedge, I is very much small, thus r is very much small. Okay, here if r is very small, cos r tends to become 1 because angle of wedge is very small. If the angle of the wedge is very small, only then we get these assumptions and considerations. Thus, the path difference can be approximated from 2 mu t cos r to 2 mu t. Now, in this picture, you can see the apparatus of the air wedge. We have two plain glass plates, right? They are held together on one end by a rubber band. And on the other end, we have a thin paper, a very thin paper placed between these two glass plates. If the glass plates are arranged in such a manner, a very thin medium of air will form a wedge-shaped film between these two glass plates, forming an air wedge. And if we look into this air wedge using monochromatic light, we happen to see interference patterns. The pattern observed will be of this manner. Now, by using a traveling microscope, we can select any one of the fringe as the nth fringe. Okay, and the successive fringe will be the n plus 1th fringe. So we usually take the dark fringes for counting because that is the most suitable fringe to select. Now let us try to calculate the fringe width between these fringes. The distance between any two consecutive fringes is called its fringe width, and let us try to calculate it. From this fringe width or from this interference pattern, we can in turn calculate the angle of the wedge. Now let us assume an air wedge formed by placing two glass plates one upon another and a thin wire at one end. Let the diameter of the wire be small t, and let this make an air wedge of angle theta. Thus, we can see an interference pattern of this nature, where we see alternate bright and dark fringes of equal width placed equidistant from each other. The distance between consecutive fringes is called the fringe width beta. Now let the distance from the closed edge to the thin wire be xn. So let us assume we see a dark fringe at that position and let the distance be xn. And let the distance from the closed edge to the next consecutive fringe be xn plus 1. Okay. So here we have tan theta, that is opposite side by adjacent side. Tan theta becomes t divided by xn. Thus, t is equal to xn times tan theta. Now, at the nth dark fringe, the condition for destructive interference is satisfied. Hence, 2 mu t is equal to n lambda. Substituting for t, we get 2 mu xn tan theta is equal to n lambda. Let this be the first equation. Now at the n plus 1th dark fringe, we have the condition 2 mu x n plus 1 tan theta is equal to n plus 1 lambda. Let this be the second equation. The second equation minus first equation gives 2 mu into xn plus 1 minus xn tan theta is equal to lambda. Here, the term in the bracket is the fringe width. That is 2 mu beta tan theta is equal to lambda. Thus, beta is equal to lambda divided by 2 mu tan theta. Now, if theta is small, the angle of the wedge is small, tan theta is usually approximated to theta. Hence, we can write beta is equal to lambda divided by 2 mu theta. And this is to be studied. This is of importance. Beta fringe width is equal to wavelength lambda divided by 2 mu theta, where mu is the refractive index of the medium of film and theta is the angle of the wedge. Now here we see the interference pattern upon an air wedge. We know that fringe width is equal to lambda divided by 2 mu theta. That is, fringe width does not depend on the order of the fringe n. Hence, we understand that fringes are of equal thickness. Now, fringe width beta is directly proportional to wavelength lambda. So, if you use a blue colored source light, the fringes will be very close to each other. Whereas if you use a red colored source light, the fringes will be a bit more further apart from each other. So for practical purposes, for simplicity in viewing, we use sources of longer wavelengths. Now fringe width beta is inversely proportional to wedge angle theta. That is, if the wedge angle theta is small, fringe width will be larger. And if wedge angle theta is large, fringe width tends to become lower. That is, fringes tends to become closer. Hence, for practical applications, we usually select air wedges having wedge angles very small. That is, very much less than 1 degree. Now, what happens when white light is incident on an air wedge? Till now, we had been seeing this air wedge through monochromatic light. Now, what happens when white light is incident on an air wedge? We see a pattern like this upon this air wedge. So at the closed end, it will be dark in color, and from there we see a colored pattern varying from violet to red. And at the other end, towards the other end, the colors all overlap over each other, and hence the film appears white. So the edge of the film appears dark. The dark edge is followed by a colored pattern from violet to red, and towards the region of larger thickness near the sample, film appears uniformly white where no fringe pattern is observed. Now, why do we see colors on thin films when it is viewed in white light? We see this in our everyday life. See, uh, for us, for an observer, the thickness of the film and the angle with which we are viewing will continuously vary for the thin film. So here we usually see oil spills on the road or the soap bubbles. Okay, so throughout the film we don't see a single color. We see different colors. Okay, that is because we are viewing each point on the film at different angles. So let us assume a film of this sort. See, a thin film, it can have varying thickness. Okay, so a thin film can have variable thickness. On practical cases, the thickness will vary. Okay, so T varies, and also when light falls upon it, because of the varying thickness, it will get reflected in different angles. Okay, also the reflected light from the bottom surface of the film will also be reflected at different angles. So here, since R is continuously varying, we get colored patterns. Okay, since T and R are varying randomly, the conditions of interference also vary in a random manner and we see colored pattern. At some points, the rays constructively interfere to give a particular color, whereas at other points, the rays destructively interfere to remove the particular color and give the complementary color to our eyes. Okay, so when destructive interfere happens, only that particular wavelength will be absent. All the remaining colors will reach our eyes, and that forms the complementary color. Okay, so today we have gone through interference of light on an air wedge. That's all for today. Thank you.